When you think about geology, the one thing that pops in your head will be rocks. Rocks are very common in our daily lives. We see it along the road, within parks, or even the mountains that towers the horizon. But often we don't really understand what they are or what they are made of. Today, I'm going to give you a brief journey about rocks and minerals. Greetings, my name is the Magnetic Sage, and this is Geology Made Easy. So you might be wondering, what are rocks, what they are made of, and what makes them gosh darn special? Rocks, also known as stones, are any naturally forming solid aggregate of minerals or mineraloid matter. To make things simple, they are just a bunch of minerals or mineraloid glued together without any help from human processes. But before proceeding into rocks, we need to dissect it into its core components, which are the minerals. So, what are minerals then? When you hear about minerals, you would often think about gems, diamonds, jewelry, and probably the one famous
Shungite. Rocks. Do you know what shungite is? Anybody know what shungite is?
well, those are examples of minerals. They are not the definition of it. So, the best way to describe what minerals are with this acronym. NIDO. It is short for naturally occurring, inorganic, homogeneous solid with definite chemical composition and ordered internal structure. A more scientific description for minerals is based on the International Mineralogical Association post in this image. The International Mineralogical Association has established the following requirements for a substance to be considered a distinct mineral. It must be a naturally occurring substance formed by natural geological processes. It must be a solid substance with its natural occurrence. It must have a well-defined crystallographic structure, and it must have a fairly well-defined chemical composition. To give a perspective of which are minerals, we will have a short quiz. Which of these are minerals? Have you guessed it? Well, only these are minerals, and these are not. So you might be wondering why so. Let us delve right in. Icebergs are natural ice. They are inorganic because they are not produced by any organisms. It is homogeneous throughout, which is solid, and it has a definite chemical composition, which is H2O, and it has ordered internal structure. Natural salt checks out as well. It's natural, inorganic, homogeneous solid. Its chemical composition is NaCl or sodium chloride, and it has an ordered internal structure. So what about these three then? Well, pearl is naturally occurring and an homogeneous solid, but it's organic because it's both aragonite or a form of carbonate and proteins which contain CH molecules. Refrigerated ice is inorganic, homogeneous, has definite chemical composition and an ordered internal structure. But it's not naturally occurring. We humans make them every day to produce a cool glass of lemonade, or whatever beverage you prefer. And finally, obsidian or volcanic glass. The famous dragon glass in the series Game of Thrones. It's naturally occurring, inorganic, homogeneous, solid, and has definite chemical composition of SiO2. But looking at it microscopically, it is amorphous, meaning it doesn't have ordered internal structure. Therefore, these three belong to a category called mineraloids. A mineraloid is a naturally occurring mineral-like substance that does not demonstrate crystallinity. Mineraloids possess chemical compositions that vary beyond the generally accepted ranges for specific minerals. Additional known examples of these are coal, shungite, anthracite, jet, petroleum, which are all carbon-based mineraloids, water, and amber, to name a few. So how do we know what minerals and mineraloids are? Let us delve into how these are being studied and described by geologists. Minerals are generally classified qualitatively or using descriptive means. It can be by a hand sample visible by the naked eye, via a special microscope called petrographic microscope, or via an electron microscope to know its crystal structure. Though minerals can also be classified via quantitative means, such as using chemical analysis via X-ray fluorescence or via crystallographic analysis using X-ray diffraction. For now, we will stick to the basics and focus on the hand sample approach for classifying minerals. You can analyze minerals based on the properties such as color, streak, hardness, luster, habit, cleavage, fracture, effervescence, specific gravity, and magnetism. Let us define each. Starting with color. Color is self-explanatory. A mineral can have multiple colors, or different minerals can have the same color. Streak is the color of the mineral when it's in powdered form. In geology, it is common to prefer streak than color in identifying minerals. This is because streak does not change. On the other hand, as mentioned earlier, the color of a mineral can change based on impurities or atoms that aren't originally part of that mineral. Different minerals can also have the same color but have different streak. Hardness is basically just how a mineral is resistant to scratching or abrasion. The common scale being used is Mohs hardness scale, shown in this image. The softest being talc and the hardest being diamond. Luster is how light looks like being reflected on the mineral's surface. The common adjectives used to describe luster are the following: metallic, submetallic, non-metallic, vitreous, dull, greasy, pearly, resinous, silky, waxy, and adamantine. Habit or crystal habit is the tendency of a mineral to grow to a certain shape due to its atomic structure or sometimes due to their environment. Some examples of habit are botryoidal, like malachite and hematite, banded, such as rhodochrosite and fluorite, striated, like tourmaline and beryl, acicular, such as rutile, malachite, and tourmaline, dendritic, such as copper and pyrolusite, nodular, such as quartz, azurite, and hematite, and prismatic, such as quartz, beryl, and tourmaline. Cleavage and fracture. Cleavage is the tendency of a mineral to retain a certain shape after it breaks. Generally, we are interested in the number of directions of a cleavage and their angles. To give an example, biotite mica has one directional cleavage, and pyroxenes have two at 90 degrees, while amphibole has also two, but at 124 and 56 degrees. Meanwhile, fracture is the characteristic mark left when a mineral chips or breaks. All minerals exhibit fractures, but not all minerals have cleavages. Examples of fractures are conchoidal, uneven, hackly, splintery, even or smooth. Effervescence is the ability of a mineral to dissolve when exposed to hydrochloric acid, or HCl. Also known as acid test, this is used primarily to indicate the presence of carbonate minerals such as calcite and dolomite. When HCl is dropped to a calcite sample, it fizzes, and this can be described by its chemical formula presented on this image. Specific gravity is a measurement that determines the density of minerals. It's the ratio of the weight of the mineral to the weight of water. The specific gravity of water is 1.0. When a mineral has a specific gravity of 3, it means that it's 3 times heavier than water. Generally, minerals with specific gravity under 2 are light, between 2 to 4.5 average, and greater than 4.5 are considered heavy. To give an example, graphite has a specific gravity of 1.75, quartz has a specific gravity of 2.65, and magnetite has a specific gravity of 5.17. And lastly, magnetism. Certain minerals have the ability to exhibit a magnetic field. This is due to their chemical structure. Generally, there are 3 magnetic property types. Ferromagnetic minerals have strong attraction to magnetic fields. Examples are magnetite and pyrrhotite. Paramagnetic minerals have weak attraction to magnetic fields. Examples of which are hematite and franklinite. The only diamagnetic mineral who repels magnetic fields is bismuth. The characteristics mentioned are the ones generally used in hand-sized samples of minerals. Again, geologists can further classify and describe them using techniques such as mentioned earlier, X-ray diffraction, and a petrographic microscope for further identification of the minerals, which will be discussed later on. Now that we have a brief overview of what minerals are and how they are described, we can proceed to their aggregated form, which are rocks. Again, rocks are defined as the solid aggregate of minerals and mineraloids. There are 3 divisions of rocks: igneous, sedimentary, and metamorphic. Igneous rocks are the rocks that form from the cooling of hot molten rock. This molten rock, called melt, are derived from deep within the earth. The origins of these magma or molten rock will be discussed in a later video. The melt can be classified into 2. Magma is the molten rock beneath the Earth's surface, while lava is the molten rock extruded and flows on the surface of the Earth. Igneous rocks can be divided into 2, intrusive and extrusive. Intrusive igneous rocks form when magma cools and crystallizes underneath the surface. They cool for a long period of time, typically millions of years, and form large crystals that can be seen in the microscope and even in hand sample. These textures are called phaneretic. Extrusive igneous rocks form when magma cools and crystallizes on the surface of the Earth. They cool for a relatively short period of time, typically down to hours or minutes, and form small crystals. These crystals can be hard to observe in hand sample and requires a microscope to be seen. The ones that cool very fast, seconds even, produce volcanic glass, which are very minuscule even under the microscope. These produce a glassy texture in the hand sample, an example of which is obsidian. There are certain common rock-forming minerals that form igneous rocks. The best way to visualize these minerals are based on the Bowen's reaction series. The Bowen's reaction series describes how certain minerals form under different temperatures as the magma cools. In the figure, there are 2 series. First is the discontinuous series, which starts with olivine, then pyroxene, then amphibole, and then biotite. The second is on the continuous series, which is mainly plagioclase feldspar. High temperature feldspars are calcium rich, while the lower temperature ones are sodium rich. As the temperature falls even further, these 2 series merges, forming alkali feldspar, muscovite, and finally quartz in that succession. These minerals are then used to further classify igneous rocks using the color index shown in this image. The main categories are felsic, intermediate, mafic, and ultra-mafic rocks. Next, we go to sedimentary rocks. These rocks are made out of pre-existing rocks or living organisms that were derived from sedimentary processes. These processes include erosion, weathering, transportation, deposition, diagenesis, and lithification. Sedimentary rocks are generally classified into 2: detrital or clastic, and non-detrital or non-clastic sedimentary rocks. Detrital sedimentary rocks are primarily due to the mechanical breakdown of pre-existing rocks. The wooden 1/4 grain sized scale is the widely used standard for objective description of clastic sediments. The largest particle size is called gravel with sizes greater than 2 mm. Sand is the intermediate size between 2 mm and 0.063 mm. And finally, the smallest is scale or mud with less than 0.063 mm. Under the non-detrital rocks, there are biogenic, biochemical, and chemical rocks. Chemically derived sedimentary rocks are primarily precipitated from fluids, examples of which are rock gypsum and rock salt. The best example for non-detrital sedimentary rocks are limestones. These can be chemically derived, but it's primarily biogenic in origin. The classification of limestone deserves its own separate video because there are so many classification schemes that are being used for it, such as Lukrembo and Dunham, to name a few. And finally, metamorphic rocks. These are rocks which are originally from a pre-existing rock such as igneous, sedimentary, or even an earlier formed metamorphic rock, but are then subjected to different temperature, pressure, and hydrothermal fluids to transform them into another rock. Do not confuse this to an igneous rock. Metamorphic rocks are not melted or broken down. They are just simply transformed into a more dense, compact version of themselves, which contain new minerals. An example of which is granite, when subjected to high temperature and pressure, can metamorphose into gneiss. Generally, metamorphic rocks can be classified into two: foliated or non-foliated metamorphic rocks. Foliation is a texture in metamorphic rocks which shows a layering pattern. This is due to the preferential orientation of minerals after being subjected to pressure-temperature changes. Under foliated metamorphic rocks, you have slate, phyllite, schist, and gneiss. Under non-foliated metamorphic rocks, you have marble, serpentine, and quartzite, as an example. There are different ways to classify metamorphic rocks. It can be classified based on their mode of metamorphism, such as contact, regional, dynamic, and impact, or based on their mineral assemblages or facies, such as burial, green schist, eclogite, and etc. Overall, the three rock types discussed earlier makes up the rock cycle. It's amazing how rocks, simple as we think previously, can have complex and deep information about them. With this knowledge about rocks and minerals, geologists try to understand how the Earth is structured, how the Earth changed over time, and how knowledge of these processes can benefit us in other fields such as mining, engineering, and technology. If you like this video, please don't forget to hit the thumbs up, comment down below your thoughts, and don't forget to subscribe to the channel. Thank you.